All right, hello. We talked about the general set theory. So today we're going to start talking about probability. Do some fixing of self. All right. Okay, so probability is a topic in mathematics that's the people study a lot from a long time ago. It has something to do with money. People like gambling, and the probability is very important in gambling. And here, right now in modern world, probability is even more applied in many areas. I show you two very simple problems. We're going to use the two models to solve these two problems. The first one is about winning the number of lotteries, winning the number of winning lotteries. If you buy a particular number of lotteries, say the probability that you will win a winning lottery is 0.1%. And if you buy 10 such tickets, what is the probability that at least one of them is a winning ticket? I'm not going to give you the solution for the problem yet. It will be towards the end of the semester when we finish this probability part. That's about 1%. Yeah. The next problem, suppose you receive a shipment of 1,000 smartphones to sell. The factory claims that there are only about 5 defective phones in the shipment. You probably don't believe the claim, but you don't have the time and energy and the cost to check all 1,000 smartphones. So instead, you take a sample of 5, and you hold on a second. You select 10 of them and find one defective. So the question is, what would you think about the factory's claim? Do you think it's lying? At least the person is lying, or well, it's just due to some likely possibilities, something like that. We're not going to make a decision here, but we will be able to solve such problem using a claim involving probability. All right, so we will give a mathematically precise statement. The statement maybe is a little bit vague. So you're going to have to say, oh, with some probability, the factory is lying. But if the probability is really high, then we are just say, oh, the factory is lying. Okay, so we needed to find out the probability that you will get at least one defective phones in the sample of 10 select from one. Assuming there are only about 5, there are exactly 5 defective phones in the shipment. So that's what we're going to do using the second model. All right, any questions so far?
No.
Thank you. Let's introduce some language about probability. I mentioned these things in the last class, maybe the class before the last class. In a random experiment, which has outcomes that are not determined before you run the experiment. So we call them random experiment. And each running would be called a trial, and each trial has some outcomes. And the sample space is a set of all possible outcomes. An event is a subset of sample space. Okay, so this is the language. Let's have a look at a simple example. If we are toss coin 3 times, what is the sample space if the outcomes are such as HHH? So 3 heads. All right, so here one trial is tossing a coin 3 times. Okay, it's not tossing 1 time, it's actually tossing 3 times. It's one trial. We're trying to figure out the sample space, right? We're trying to figure out all the possible outcomes. Can anyone tell me a couple more? Do I see anything on the chats?
Like different outcomes, you mean?
Yes, exactly.
You could have TTT.
All right. Who's that?
Me?
Yes.
It's Lindsay. What's up?
Oh, it's Lindsay. Hi.
How you doing?
Good, good. So you say TTT. Very good. Miak was saying TTH. Okay, very good. Do you know how many of them? Anybody? All right, THH. How many of them totally? Does anyone know? Let's do THT and T. Maybe I should list them in a nice order. Let's do it again. This makes me a little bit dizzy. Usually I organize the way I write. So let's start with TTT. Okay, so 3 T's and 1 H. So TTH, and let's change the position of H. All right, that comes with that's fine. Okay, 1 H. And then we have 2 H's, THH, HTH, HHT. And then we have 3 H's. Okay, this is one way of ordering them, listing them. Totally, there are 8 of them. Yeah, so this is the sample space. And we can talk about the event E to be the set of the events, the outcomes that have 2 heads. Yeah, that's the event. And now we can talk about 2 heads. So THH, HTH, and HHT. All right, so that's an event.
Yeah, I think it's Tuesday as well. Oops, my bad.
All right. We call 2 events mutually exclusive or disjoint if their intersection is empty. So E and F are mutually exclusive. Or disjoint if E intersect with F is empty. If we draw a Venn diagram, then there will be no intersection. So you have E here, you have F here. Yeah. That's the sample space S. Sometimes we use U as universal set. We are talking about probability, so I tend to use S for sample space. You can use U, it's fine. And we use S a lot in different situations, so maybe a little bit confusing, but within the context, it should be clear. All right, so these are 2 events that are mutually exclusive or disjoint. So in this example, toss a coin 3 times, we can talk about events E, which has 2 heads. The set of outcomes with 2 heads, and F 1 heads. Now, I'm not sure if we use one heads or one head. Let's do that. Then they are mutually exclusive. Okay. If we talk about two events like that, so E is H. There's one H, at least one H. At least one heads. Heads. F is at least one tail. Tail. Then they're not mutually exclusive because you could have one head and one tail. Okay, so they're not mutually exclusive. Okay, so I want to introduce the concept of probability. There are several different meanings of probabilities in the concept of probability. Sometimes it's sort of random frequencies. You toss a coin and you toss a coin 100 times, you got 49 heads. So 49 out of 100, we're going to define this to be the probability of getting heads. And if you toss more and more and more, the limit will be the probability of getting heads. Okay. So this is kind of limit of relative frequencies. Another way of looking at the probability is like personal probability. Say, oh, I think the chance I'm gonna get an AA in this class is 90%. So you're not going to take a lot of times. So it's difficult to get the exact sense of probability, but we do say that, so it's kind of personal probability, subjective. In mathematics, we give a formal definition of probability. It looks abstract, okay, but really tells the principle, the features of the probability. So we call a function of probabilities. A function is defined on a sample space. We are okay with the language. Maybe it's not really exact if we go to high level math, but for the moment, it will be okay. So probability is a function defined on the sample space. If it's called a probability if it satisfies three axioms. So P defined on the sample space S is a probability function. That's fine, probability. If three things. One, probability of any event should be always greater than or equal to 0 and less than or equal to 1. Okay. We don't talk about negative probabilities. We don't talk about probabilities that are greater than 1. We make it a rule. It's an axiom. Second, we require the probability of the sample space to be 1. That means everything in the sample space are observable. Okay. The third one, the probability of E union with F is the sum of the probabilities. But that's actually not true in general. So there's a big if here. If E and F are mutually exclusive. All right. We will introduce a more general rule, which is called a union rule or addition rule. It takes care of the general situation. This rule is an axiom, but it only deals with the case when the two events are mutually exclusive. However, that general rule is actually obtained by using this axiom, even though it's more special. Okay, there's a condition here. So we don't list the union rule or addition rule as the axiom. Instead, we use this rule as one of the three axioms. So any function defined on S, the sample space, if it has satisfied these three conditions, we can call it a probability. All right. So especially this one, if you give me a probability that is greater than 1 and something is wrong, you should check your answer. If you cannot figure out the mistake, at least you should say, hey, I don't know, I couldn't, I know it's wrong, but I don't know how to fix it. But at least you know the concept. If you give me a probability 2.3 without saying anything, that's really not good. Okay.
What does the second one mean again?
Oh, the second one is the probability of the sample space is 1. So the probability of everything happening, all the possibilities add together will be 1. In reality, that may not be true. Say in the universe, there's something we are not able to observe, like black holes, inside black holes. So in that case, the probability of everything in the universe is not really 1. There are different ways of defining a probability in that way, in that sense. But here, what I just assume the probability of the sample space is 1. Okay. It's very useful when we try to find the probability of a complement. The second rule is called the complement rule. We're going to introduce 3 rules in this class, 3 rules of probability. So the probability of the complement, how can we figure out that? We know E complement and E itself, they are mutually exclusive. Okay, so the probability of the the union of these 2 sets will be the sum by using the third axiom. But this one, because the union of the complement and itself is the total, is the sample space, which is 1. Now we know the probability of the E complement equals 1 minus the probability of E. All right. In order to get this complement rule, we would need this axiom. Okay, so far so good.
Yeah.
All right. There's one thing I want to introduce before I move on to examples. There's a condition called equally likely condition. This condition basically says you have a trial and each outcome would be considered to be equally likely. Okay. Especially there's some situations like you roll a die twice and you have 36 outcomes when normally we assume they are equally likely. So the probability of getting each pair would be 1 out of 36. This condition, we need to be very careful. This condition is we usually add it onto the sample space. It's not always assumed. For example, you toss a coin 3 times, right? And we consider the number of heads in 3 tosses. Now we're talking about the number of heads. So the sample space is not those HHH. Instead, it's the number of heads. So you could have 0 heads, 1 head, 2 heads, 3 heads. These are the possibilities. And these outcomes are not assumed to be equally likely. So instead, these things would be considered to be equally likely if we are tossing a fair coin. Okay, if the coin is fair, then the probability of 2 heads or 3 heads would be the same as the probability of 2 heads and 1 tail. It's the same thing. I'm HHT. I'm not saying the number of heads is 2. Actually, that's slightly different. quite different. So we assume these outcomes are equally likely. However, here, we're not assuming they're equally likely. In fact, they are not. It's more likely to have these outcomes than 0 and 3 if coins is fair. All right. A common mistake I hear from students, from people actually, is that two outcomes, so equally likely, half chance. That's not true. Okay, that's not in general not true. For example, you have a box which has 3 black balls and 2 white balls, and you select one of them. All right, so the outcomes, there are only 2 outcomes. One is black, the other one is white. However, they are not equally likely. So the probability of getting a black ball is 3 out of 5. The probability of getting a white ball is 2 out of 5. Okay, so you see 2 outcomes. Normally, you should not assume they are equally likely. But sometimes we do. For example, you toss a coin, we naturally assume they're equally, it's fair. We naturally assume they're fair if it's not specified. Sometimes we do specify the probability of heads is 3/4. Then it's not fair. Okay, so this condition, under this condition, an equally likely condition, the probability of an event equals the number of elements in the probability divided by the number of elements in the sample space. So for example, here, not HH, so for this problem, what is the probability that you have 2 heads? Exactly 2 heads. We just listed them, there are 4 of them, right? So you have 4. 2 heads, hold on a second, 3 of them actually. Okay, did I make any mistake when I listed 2 heads? Why I vaguely remember I had 4 of them. 2 heads should be 2 HHT, HTH, and THH, the 3 of them. We do assume all these outcomes are equally likely, and 8 of them. So you have 3 out of 8. Okay. So you count how many of them, how many elements are there in the event, and divide by the total number of the outcomes in the sample space. I think I'm done with the introduction about language and some conditions. Any question about these concepts? All right, we move on to some examples. We're gonna use some toy models. In probability, we use coin tossing. It's about a toy model. We use dice, and balls, and another one is the card. In probability, we usually study a standard deck of 52 cards. We usually don't include 2 jokers. Okay, so we have 52 cards. If you're not familiar with cards, here's a picture. Please try to get used to it. I think you have seen it, but some of you don't play cards and you're not familiar with them. So I may put problems in the exam, so you need to know what cards are. So a standard deck of 52 cards has 4 suits. And this one is called club. This one is called heart, and spade, and diamond. Each suit has 13 cards from 1 to 10, and then you have a face cards. So these are face cards. And these are face cards. And these are the red cards. These are the black cards. Okay. All right, so let's work with some simple questions first. So what is the probability of getting, or you select one card from these cards, and select one card. What is the probability that that card is a face card? I want everyone send me an answer through chat, so I know you are here. I would take attendance, all right? All right, I got 2 people. Oh, I need a probability. So where did that come from? Ah. Ah, 12 out of 39. Okay, you changed it. 0.21. Do you have any solution for that? 23%. 12 out of 52. 12. Okay. So, well, I'm still doing the handles. Okay, so we count how many face cards. I have 1, 2, 3, 3 times 4, you have 12. Totally, you have 52 cards. Simplify it. 13, 3 out of 13. All right, so that's the probability of getting face card. What is the probability of getting let's do a little bit trickier one. A face card. Oh, not that tricky yet. Let's find the probability that a card is a black number. So not a face card, it's a number card. Ace is a number card, it's 1, okay? Black number card. What is that? Okay, I got one answer from Jasmine. A black number card. Black clubs are also black. So we have 20 black cards out of 52. We don't 26. Why we have a 5 over 26? Two people got 5 out of 26. Oh, okay. Here we're still selecting a card from a standard deck of cards. We're not selecting a card from black cards, okay? That's the concept of conditional probability we will be discussing later on. All right, so that's 5 out of 13. Okay. So 20 out of 26, that's the probability of selecting it's a black numbered card. If the card is selected from black cards. There's an if here, this is a condition. So it's called a conditional probability. That will be discussed slightly later the next class. So this is the condition for given information. All right, next one. Let's find the probability a card is a club or 10. What is that? So that one is a little bit trickier. So I want you to think about it and then try to answer me. Okay. Yes, 10 is number 10. Okay, so I got an answer. I'm gonna list some of the answers I got. I got 14 out of 52. I got 4 out of 13. I'm not saying the right answer, but I'm listing them, okay? So this number comes from 16 out of 52. Can I have a different answer? Yes, face cards are considered to be, or if they're club, then they are clubs. Okay. All right, I got another answer. 17 out of 52. Okay, so let's count how many of them. Club or 10. So that's a union, and that's a union. So club should be there. We have 13 clubs. 13 clubs. And then we have 4 tens. Okay. So seemingly 13 plus 4, but this one is double counted. We need to subtract. So it should be 16 out of 52. We have a winner here. All right. I think 2 people got it all right. Or 4 people. Sorry, 3 people. Okay. That one, we use the either we use the principle of inclusion exclusion, or the next I mean the rule we're going to introduce slightly later. It's called the union rule. It's a club plus the probability of having 10 minus probability of getting club 10. Club and 10. Okay, so club is 13 out of 52. 10, you have 4 of them. For the moment, we don't exclude anything, but then subtract the double counts. Okay. All right, so let's introduce that rule. Where's the rule? It's gone. Not there. That's fine. What is the title? There's so many things on the screen. I cannot really tell. Okay. So let me introduce the union rule or addition rule. Says the probability of the union of 2 events is the sum of the probabilities minus the probability of the intersection. Okay. Similar to the pi inclusion exclusion, we can draw a Venn diagram, and then it's very clear that there's this intersection, things get involved. So you have a 1E, 1F. It's a sample space. You have E here, you have F here. So the union would be this union with this union with this. Let's call it piece 1, piece 2, piece 3. So the probability of E union with F equals the probability of piece 1 plus the probability of piece 2 plus the probability of piece 3. We are using the third axiom of the probability. And these three pieces, 1, 2, 3, they are mutually exclusive. Okay, they're mutual, even though they look like that, they're mutually exclusive. There's no intersection. Okay, the intersection is empty. So 1 plus 2, that's the probability of E, but then 3 would be the probability of F minus the probability of 2. So that's okay. So that's the addition rule. All right, let's work with another toy model. We roll 2 dice, assuming they're fair dice, fair. And we assume they are equally likely. So they are equally likely. Okay. What's the probability that you see either a 3 or a 5? It doesn't specify which number is 3. The first one is 3, or first one is 5. Okay, either 3 or 5. One way of doing that is just count. Okay, so we count. Oh, there's a 5 here. There's a 5 here. There's a 3 here. And there are 3 here. So count how many of them. 1, 2, 3, 4, 10. 1, 2, 3, 4, just 20. 20 out of 36. Okay. Another one, actually a little bit more complicated than I was expecting. So another way, you're gonna have let's say the probability of a 3. There's 1 3. I mean, I'm not saying there was 1 3, actually, at least 1 3. There's a 3, possibly 2. Okay. So maybe what I should say, either a 3 or a 5. Hey, when I say either a 3 or a 5, what do I mean? It's not very clear, huh? Let's specify. Either a 3, so do we allow 2 3s? Available. Either a 3 or a 5. What do I mean? I'm not sure what I mean by that. Either, how do I say that? Just once you see a 3 or you just see a 5, then it's included. But I don't want to specify 1 3. How do I say that? Either a 3 or a 5, would that be okay? Not exactly one of them. That's what I mean. So maybe I should say either at least 1 3 or at least 1 5. That would be clear. Okay. Okay, that's what I mean. So this is 20 out of 36. Okay, so that's people agree. All right, good. It's a little bit tedious to write these letters, those words. So I'm gonna just call this thing A, and this thing B. Okay, so you have a union A union with B. And that's probability of A plus the probability of B minus the probability of A intersect with B. It's a little bit complicated. Probability of A is at least 1/3. There's another layer of pi there, union rule there. At least 1/3. So you have that. Okay. So you have 11 of them, right? 11 of them. But in order to use, if you don't count, then you have to use the addition rule again. So like the probability of, maybe I'll just do that. 1 out of 6 plus 1 out of 6 minus 1 out of 36. I'm using that again. And then for probability B, which is at least 1/5, it's the same. And then probability of A intersect with B is at least 1 and at least 1/3 or at least 1/5. We have 4 of them. Okay. And it's an and. Hold on a second. That's not good. At least 1/3, at least 1/5, only 2 of them. So you have 2 of them. Yeah, this problem is a little bit more complicated than I was expecting at the beginning. All right, anyway, let's calculate it. 11 out of 6, 36, plus 11 out of 36, minus 2 out of 36, still 20 out of 36. Okay. That is a union rule. Let me give you another example. What is the probability that at least one of the number appears? Okay, at least one of the numbers appears. One is greater than or equal to 3. Okay. One way of doing that is it's at least, right? It's a union. So let's call the first die. The first die is greater than or equal to 3. B is the second die is greater than or equal to 3. So we're looking for the probability of the union. Okay, at least one of them is greater than or equal to 3. At least A or B. So that is union. That's the probability of A plus the probability of B minus the probability of A intersect with B. Okay. So probability of A, that means the first die is greater than or equal to 3. First die is greater than or equal to 3. That's these things. And that's these things. It's already 12 o'clock. Let's continue a little bit, then we pause. Anyway, start. We're gonna have a 30-minute. No, hold on a second. We can debate. Let me continue for a minute and finish this problem, and we talk about how we approach. Either we have a shorter break and leave earlier, or you have a 30-minute and normally like normal time. Okay, so probability of A, how many of them? First one is greater than or equal to 3. So you have a 24 okay, out of 36. And then the second one is at least is greater than or equal to, actually greater than equal to. So you have that. All right. Again, you have a 24 out of 36. And then minus both are greater than or equal to 3. Both are greater than or equal to 3. You have so many of them. That's 16 out of 36. $48, $32. All right, so this is one way of doing that. Another way, we consider its complement. If at least one is greater than or equal to 3, its complement would be neither is greater than or equal to 3. So both are less than 3. So less than or equal to 2. Okay, so 4 of them. So it's also equal to 1 minus 4 out of 36. Okay. That's the second rule I want to introduce, which is called the complement rule. I said something already earlier. Probability of the complement equals 1 minus the probability of E, or probability of E equals 1 minus its complement. They are exactly the same as the rule. Okay, so sometimes it's very easy to use to find the complement, find the probability of complement. Then you use the complement rule. We can show from the Venn diagram. And so you have E here, you have F here at the sample space. The union is here. So the probability of the union, and it's 1 minus the probability of outside. It's neither. So maybe I should say this instead of writing we say, how do I say that? E or F, E or F, that's a union. 1 minus the probability of neither E nor F. That's an E complement, intercept is a complement. This is the union. And so here, this example, we have the probability that at least one of them is at least 1 is greater than or equal to 3. That's 1 minus probability of neither is greater than or equal to 3. Neither is greater than or equal to 3. That means both less than 2, less than or equal to 2, which have a 4 out of 36. So that is the addition rule. Okay. So I'm going to pause, and then there's one more example I want to talk about, and then we continue to the new material. I wanted to finish as many materials as possible today, and then we have more time on practice. Okay. All right. So what are we going to do? I'm going to pause for the moment and decide we have a shorter break or not. All right, let's have a look at an example. Let's do some editing. Pause. So have a look at this example. Susan is a college student who receives heavy sweaters from her aunt at the first sign of a cold weather. She is loved. Susan has determined that the probability that the sweater is the wrong size is 0.47, and the probability that it is a loud color is 0.59. And the probability that it is both the wrong size and a loud color is 0.31%. Oh, 31%. Find the probability that the sweater is the correct size and not a loud color. A better way, I mean, you can work it out using argument. It's not wrong, but a straightforward way for, especially like for me, is to use Venn diagram. So let's draw the Venn diagram. Okay, you have two types, wrong size and loud color. And you have all the sweaters. That's the sample size, not the sweater. But they could be the same. Wrong size and a loud color. The probability that the both would happen is 0.31. So the rule of thumb, you start with the middle part, the intersection. And then the wrong size is what? 0.47. Minus 0.31, you get 0.16. Okay. Again, I wanted to emphasize, do not put 0.47 here. Okay. The 0.16 is the probability that sweater is only the wrong size, not louder with louder color. Okay. Similarly, for loud color only, 0.59 minus 0.31, so you have 0.28. And then you find the good ones, right? Not the wrong size, nor the loud color. So you have a 0.16 plus 0.31 plus 0.28, and the outside 2.25. Okay, so now our task is to figure out the meaning of what the question is asking. So find the probability that the sweater is the correct size and not a loud color. And, okay, it's intersection. So let's do that. Correct size, not the wrong size, and not loud color. Well, actually, it's the good ones. So they are the good ones, which means outside. Okay. So you can directly say the answer is 0.25. You show the Venn diagram, then you show steps and details, and we would accept the answer. Without the Venn diagram, the answer is not very good. I want to see some more evidence. Okay. Next one, find the probability that the sweater is the correct size or is not loud. So correct size, 4G. Let's say of a correct size or not loud. Correct size is the complement of the wrong size. Okay. It's a little bit hard to to argue, to make a reason, really not very easy. So let's just work with Venn diagram. It's just easier, I guess. But you do need to work this out. That's probably not easy as well, but I hope you could do that. Okay. So W complement. So the correct size, everything outside W would be included. And everything on the not loud. Not loud, so you will have that. Now we are looking for the union, not the intersection. So everywhere that is shaded, it would be included in this. So the answer would be 1 minus 0.31, 1 minus 0.31, which is 0.69. Okay. We introduced the De Morgan's laws, which is equals the intersection. And the law goes like this, but obviously it's equation, and you can go from left to right, from right to left, doesn't matter. Okay. So the probability of the union of the complements is 1 minus the probability of the intersection. I'm using the complement rule here. All right. If there are only 2 sets, well, sometimes 3 sets, but we don't usually test you for 3 sets. This kind of problems, we sometimes call it Venn diagram problem, because you usually are able to solve the problem in drawing Venn diagram. Sometimes you incorporate the rules, the probability, well, union rule, complement rule. But I think Venn diagram is probably very illustrative, so you probably should learn how to use that. Any question about this problem? Okay. I don't get any response, so I'm not sure if you are here.
No questions.
All right, thank you. All right, let's move on. We're going to cover new materials, okay? New concepts. Somebody mentioned something earlier about drawing a card that is black numbers, and somebody got 20 out of 26, right? That is what I mentioned earlier was a conditional probability. So here I wanted to motivate the concept as well. I wanted to argue that this conditional probability is really commonly used in our sense, in our human sense. So one example I showed here is that what if somebody asks you the probability that you get stuck in the O'Neill tunnel, the instinctive reaction would be when. Okay. They say, oh, it's rush hour, then the probability is probably more than 99.9. But if it's midnight, then the probability is quite low, maybe, I don't know, 1%. All right, occasionally there's a work there. So that kind of probability is called conditional probability. So we could say something like this: oh, the probability is gonna stuck in the tunnel. The probability, okay, given that rush hour. Oh, this is a notation we say it's given, or we say knowing. rush hour, that is almost quite sure, 99.9. And then the probability stuck in the tunnel at midnight, that's probably really low. Let's just assume it's 1%. Okay, so this is a conditional. These are the conditional probability. It's really different from the probability that you're gonna stuck in the tunnel. This question itself is not a conditional probability. Okay, it's just people think about this. Oh, you need to ask when, right? Here, this probability, you need to consider all these situations. You're gonna stuck in the tunnel when it's rush hour, stuck in the tunnel anytime. You do something about those probabilities. This is not conditional. Itself is not conditional. Okay, itself, it's not conditional, but it's just that our distinction would be considering some conditions, adding some conditions there. Those are the conditional probabilities. So another example, what's the probability that you will get an A for the course? Some people are very strong, say, oh, I don't know, I'll just get A, 90%, 99%. Some people say, oh, I need to work hard. So if I work hard, the probability of getting an A is such. If I don't study anything, then the probability of getting an A is such. So those are the conditional probability. The question itself is not really conditional probability. Okay. Another example, which when you are older, like when you buy a car, you will see that. So suppose you have a car, and you need insurance, right? Car insurance. So you call insurance company, and they wouldn't say, oh, hey, I'll give you the quote. Your premium is $600. They wouldn't do that. Probably not that expensive. Maybe okay, $200. Usually they don't do that. They'll ask you a lot of questions, right? Say your age, how many years you have been driving, do you smoke, have kids or not? This kind of things. They ask a lot of questions. What they are doing is obviously to gather information from you. So based on those information, they're gonna put you in a category of people, and then they calculate using empirical data. They're gonna calculate the probability that you will have an accident in the next year. Then they will give you a quote. Those kind of probabilities are also conditional probabilities. So what I want to say is that conditional probability is a commonly used concept. The definition we give is a little bit abstract, but I want you to make a connection. Once you reason out the definition, then it makes sense. Okay. All right, so let's look at this concept. Hey, I probably should go back before I give you this example. So what is the conditional probability? A conditional probability denoted by P of E given F. So there's a bar here. Yeah, there's a bar. Don't do this. Don't do this. It's different. We don't have this kind of notation. Okay, don't do that. Is defined by the probability of E intersect with F divided by the probability of F. We need to assume the bottom is not 0. So probability of F should be happening. What this really means is knowing F happening. If the probability of F is 0, then it won't happen. So knowing F happening is really contradictory. All right, so we don't define the conditional probability when the knowing information will never happen. So we always assume that. So this is definition. Let me explain a little bit using the Venn diagram. All right, so this is E, this is F. Okay, so E given F is If given f, what does given f mean? It means I know f happens. That restricts ourselves to the new sample space, which is this one. So knowing f, restricts ourselves on f. They have a new sample space, which is f. F happens. Anything else, I don't care. This, I don't care. It's not. I know f happens already, so we're gonna just focus on this piece. I mean, the shaded piece. Within that piece, E happens. So it's this piece over the new total. That's what it really means. The probability of the intersection divided by the probability of f. Under equally likely condition, I'll give an example which would be really illustrative. Okay, so in a class of 30 students, I usually do that. There are, let's make 14 have an iPhone. Make it smaller numbers. 14 have iPhones and 8 have an iPad. And then you have 5 of both. Okay. Now you randomly pick a person and he was using an iPad. So what's the probability this person has an iPhone? Okay, you saw an iPad already. That's the given information. So we're going to write something like the probability the person has an iPhone, knowing that this person has an iPad. Now, you know this person has iPad, 8 of them. So it's 5 out of 8. Okay, so that's using the counting argument, using assuming equally likely condition. And you divide both numerator and the bottom by the total. And then suddenly it becomes that formula. Okay, the probability of intersection is 5 out of 30. The probability of the iPad is 8 out of 30. So that's the meaning. I mean, I hope that makes the meaning of this definition clearer. Okay. Do you have any question about the concept?
No.
A screenshot of the attendance, and I'll do the attendance later. I was kind of dumb doing that in the class. Okay, let's have a look at an example. This example doesn't have a specific meaning. It's just playing with the definition. Okay, so I tell you the probability of E is 0.5, probability of F is 0.4. I dislike this number for some reason. I'm going to change that to 0.3. I think that's a way of making it like that. Okay, then I'll write it. 0.3. All right. Find the probability of E given F and probability of F given E. So probability of E given F by the definition is the probability of the intersection divided by the probability of the given information. Usually there are 2 mistakes students have. One is doing this. That is usually, it's wrong. And usually it's greater than 1. Probability cannot be greater than 1. Okay, conditional probability is a probability anyway. So it's not the union, okay? So that's wrong. Another one is that they put the wrong bottom or not even paying attention to that. That is also wrong. Anyway, we go back to this example. We try to figure out this conditional probability. And this is the intersection. All right. Sometimes people don't put this intersection sign there, but it's the intersection. So 0.3 over 0.4, which is 0.75. And the probability of F given E, you do the same thing. The intersection and a union, you can change the order of these two sets. It's the division that you can't. I mean, the conditional one, you can't, because you have a division, the bottom is different. The numerator is still the same. 5. Okay, so usually these two probabilities are different. All right, that's a 0.2, but I will probably go back to this problem. How about this problem? Probability of E is 0.5, probability of F is 0.4, and the probability of union equals 0.8. Find this and this. Both are conditional probabilities. So now you know the definition of a conditional probability. But we don't know that. How can we figure that out? We don't know that, but we know this. We can incorporate all these three numbers to come up with the probability of intersection. What rule should you think about? Any idea? I'll give a couple of seconds for somebody to answer that. How to figure that out? Anybody? What rule would involve these things? No answer? All right. So I ask, I answer, okay?
Is it addition rule?
Yes. Who's that? That's me? Who's that?
Yeah.
All right. Addition rule, yes, we have this rule, which includes all these numbers, and we're looking for this one. You have 0.8 equals 0.5 plus 0.4 minus, which is unknown, but we can solve it very quickly, 0.1. And now once we have this information, and both these two are very easy. I'm sorry, these two are very easy. So you put 0.1 here, F 0.4, 0.25. Probability of F given E, again, you get 0.1 over 0.5, you have 0.2. So this problem is a two-step problem, okay? Don't be intimidated by that. You try to sit down and think any way. All right. Come on, Apple. Any question about this, of these two problems? Let's move on. We're gonna look at the contingency table, okay, to illustrate, to treat it as an example. The manager for a brokerage firm has noticed that some of the firm's stockbrokers have selected stocks based on the firm's research, while the other brokers tend to follow their own instincts. To see whether the research department performs better than the broker's instincts, the manager surveyed missing the E here, surveyed 100 brokers with results as shown in the following table. Okay, I wanted to change right away. Okay. So this is the contingency table or two-way table. Usually you have two variables or two categories. The first one is whether the first column, whether a broker uses research or not. The other category, first row, the picked stocks that went up or not, or didn't pick stock that went up. Usually we put subtotals of the rows and columns. You have 45 people who use research and 55 who don't, and 60 people who picked the stocks that went up, and 40 didn't. And the grand total is 100. All right, so what is the probability that picked stocks that went up when research was used? 1 second. I dislike when research is used, this language. This language is a little bit confusing. Let's use if. If is more on the conditioning side. When, so it's not clear. I'm not an English native speaker. It seems to me it could be the intersection. When is probably conditioning. Intersection would be and, right? Picked stocks that went up and used research. But when is probably a bit vague on the border side. Let's put if here. So now this is a condition. Someone lets A to be a set that picked stocks that went up, B to be the set that used research. And there's a goodness of introducing variables. Otherwise, pick stocks that went up. It's a little bit tedious to write all these things. So it's A, probability of A given B. You could use the definition. Okay, A intersect with B, so you research. This is went up is A actually. Research. So A intersect with B is 30 out of 100. That's a probability. And the probability of B, that is 45 out of 100. That's 2 out of 3. Or for contingency table, it's really pretty easy to work with counts. A given B, so B is known. So this is the new sample space. Right? You're not consider this group of people. Yes. And within those 45, 30 picked stocks went up. So it's 30 out of 45. Same thing. Yeah, same like this. What about the other direction? Picked stocks, the probability that picked stocks went up when no research was used, if no research is used. If. Why don't I just change right away? Back. If and here's also if. Pick stocks that went up if, hey, what did I do? Oh. If no research was used, so it's like, well, one way of doing that is just to use the number, the counts. Maybe you hate using mathematics formalization. You just wanted to do the extinction. Okay, so pick stock that went up if no research was used. If no research was used. And went up 30, so it's 30 out of 55. You could use the formalized mathematics using A, B, and intersection, blah, blah, blah. Okay, so that is the 6 out of 11. This is 2/3. Slightly bigger than that. I think this is 4, 5. What is that? 6 divided by 11. 5454. While this one is 0.6667. So about 12% more. Anyway, those numbers, I think, just random numbers. What's the probability that somebody's picked stocks that went up and no research was used? This event, when we use this kind of language, you see this is M here, it's intersection, and you don't see no conditioning here. So this is not a conditional probability. It's not a conditional probability. So it would be simply no, went up, no research out of 100, it's 0.3. One hard part, one difficulty is that people try to figure out the English language in mathematics, whether it represents conditional probability or intersection. That's a tough thing. So I hope with some practice you will get some sense, clear sense. Any comments, questions?
I don't think so.
All right, move on. Let's introduce the concept of independence. By words, independence means, well, if two events, E and F, they're independent, what really means that whether E happens or not has no effect on the other. So for example, you roll a fair die twice, and usually we assume that the first die doesn't affect the second die, vice versa. Okay, these examples, don't look at these examples yet. That's actually quite not what I want to talk about. Okay, so let's say you go to some gambling place, Atlantic City. Say you play blackjack, and you win, you lose twice, and people usually have this instinctions like saying, "Oh, I lose two already. Maybe the next one I'll win." Okay. Well, if you assume the independence, then it's not really the case. Whether the first two win or lose really doesn't affect the third one. In reality, maybe your mood is different. That's a different story. But under the condition that they're independent, then you really you cannot conclude that the third one is more likely to be winning game. Or if you roll a die 3 times, you get 3 heads, and say, oh, the fourth one might be more likely to have a tail. That's not the case. Your roll die usually we assume independence. So knowing the first 3 all show heads, all showing heads really has nothing to do with the probability of the fourth one. That's what independence means. There are several equivalent definitions. One is probability of the intersection equals the product of the probabilities. This is usually the one you saw in middle school or high school. Say you toss a coin twice, what's the probability that you get both heads? Half times half, right? You are really assuming they're independent, or also assume they're fair coins. Another equivalent definition is this. Using algebra, it's quite easy, right? You look at the definition, you get that definition. But then if they're independent, use the first condition, which is the product. And you cancel out the probability of F, you get probability of E. So that's sort of algebraic argument from using one. There's another very straightforward explanation of this equation. Now, E and F are independent, so knowing F contributes nothing to the probability of F of E. You know information which is really useless. Okay, knowing the first toss is heads has nothing to do with the probability of the second one. So knowing this information really doesn't help. It's a redundant information. Okay, and similar one with that. These 3 are equivalent, assuming no probability is 0, because we require these conditional probabilities have no 0 bottoms. And this is probably more general because it also includes the case when the probability of E or probability F is 0. But within 130, we don't treat these things, so they are equivalent. Okay. Let's let's do what? Let's work with the first one. First example, roll a fair die twice. What's the probability that at least 1 6 is shown? We talked about that earlier using 36 outcomes, right? Here, we're not going to use that. Instead, we're going to use use what? Use union rule, but also used implied condition of independence here. We actually used that when we talked about the problem in the last class. When we say the probability of getting 1 1 is 1 out of 36, really it's implying they're independent. You know, have 1 over 6 times 1 over 6. Okay, so let's use the formula and incorporate the concept of independence here. At least 1 6. So probability is the first one is 6. Let's use S1. Or the second one is 6. This is not sample space, it's number 6. So you use the addition rule. Okay, 1 out of 6, 1 out of 6 minus. It's the intersection, it's a probably intersection is this one times. They're independent. Okay. I did say usually when you roll a die twice, you assume independence there. If it's not specified, it's always independent. So you have a 1 over 6 times 1 over 6. Yeah. So I wanted to well, I think it's straightforward, so I don't want to answer if it's ask you if it's okay. I think it should be fine. So let me move on to the formula of a union rule when independence is incorporated. So the union rule, this is always general. And if they're independent, E and F are independent. If they're independent, okay, then you have this rule. You don't really need to memorize this rule. If you understand the concept, then it's really just the union rule and incorporate with the independence. It's 1:15. I think it's a good time to stop. I didn't finish the whole section yet. There are a few things I wanted to talk about. The tree diagram and also the disjoint and the disjoint and independence. They are actually very confusing. Okay. If we say each individual concept, people understand, but once we put them together, people usually get confused. I posted a video on that, but it will be, I will give the link later when we have more when we have more practice. For the moment, we have a lot of new things, which probably are difficult for you to digest everything. So the next class, we're gonna do some practice, okay? Maybe work on workbook, or maybe you have some more examples before we move on to the workbook. Okay, that will be Monday. Any questions?
No questions.
Okay, then I hope you have a wonderful spring break. Okay, I'll see you on Monday, next Monday.
Thank you. Have a nice
Thank you.
break.
Have a good break.
Thank you.
Bye-bye.